Today we are going to discuss the frequency analysis of inverting amplifier. For inverting amplifier, I have taken the inverting amplifier. The positive has been grounded and the R1 is 2.2 kilo ohm, R2 is 220 kilo ohm. This is the input we are giving 0.1 sin omega t. Output will be RF by R1. RF is 220 kilo ohm, R1 is 2.2 kilo ohm. The gain of 100 and 0.1 sin omega t. So V0 will be around minus 10 sin omega t. And what will be our 3 dB point? 3 dB point will be 10 by root 2, 7.07. Now what we are going to do? We are just going to keep the input constant around 100 millivolt, which is equal to 0.1 volt. Now we are going to change this frequency. Now we are going to change this frequency by the function generator. These are the frequency that we will be changing. This is the column of frequency, and at each frequency we are going to jot down the output voltage. At all the frequency we are going to jot down the output voltage. Now we are going to start from 50 Hz and we will be ending at 1 megahertz. Now at 2 frequency we will be giving the most important parameter. We will be noting at 2 frequency. At certain frequency where we will be seeing that where our gain is going to reduce to 1 by root 2 times, it means 7.07. This value, this frequency we will jot down, and another extra frequency that we will jotting down that where input and output voltage are same. The input that we have applied is 0.1 volt and an output where we are going to get that 0.1 volt output around that one. That frequency we are going to check until 1 megahertz we are going to go. Now we are going to construct the circuit on the breadboard. This is the circuit for inverting amplifier. Here the biasing with the green one, the positive biasing. With the blue one we have done the negative biasing. This is RF of 220 kilo ohm. This is R1 of 2.2 kilo ohm, and positive has been grounded. From here we are supplying 0.1 sin omega t, and from here we are taking the output. Now we are going to zoom on DSO. Now if you see, the channel 1 has been set to 50 millivolt, channel 2 2 volt, and if you see the channel 1 has been set to 100 millivolt, the input has been 100 millivolt sin omega t. This is yellow one is the input, and at the frequency of 50 Hz. This is your output because this is the inverting amplifier. This must be amplified by the gain of 100. If you multiply with 100, you are going to get around 10 volt. 10.2 we are going to get, and this is inverting because of minus sign. Now I am going to change the frequency, and we are going to look at these two value, and we are jotting on this excess sheet. Now I am going to change to 100 Hz. If I am going to change to 100 Hz, then also our output voltage is 10.2 volt. Now let me change the frequency range. Now if I check at 500 Hz, now let me check at 500 Hz, the value is around 10.3 only, means it is maneuvering around 10 only. Now let me change to 1 kilohertz. If I change to 1 kilohertz, around 1 kilohertz, the value is 10.2 volt only. Now let me change to 10k scale. Now I will be checking at 2 kilohertz. Now if I check at 2 kilohertz, then the value is 10 volt. It's only the same. Now it will, I think it will start decreasing after this one. See, it has started decreasing 9.92. Now if I check at 5 kilohertz, now I am going to directly to 5 kilohertz. Around 5 kilohertz if I check, this is around 5.0 kilohertz, it is 8.8 volt. Now we are going to look at that frequency where our output is going to get 7.07 volt. Now slowly I am changing this one. See, now around 8.3 kilohertz our output is 7.07. So at 10 kilohertz we will check at the output. At 10 kilohertz our output is 6.32 volt. Now I am changing the range to 1.1 megahertz, means from now I will be checking till at 50 kilohertz. At 50 kilohertz our output has reduced, means what we are observing with the increase in the frequency our output is getting reduced, means the output amplitude is frequency dependent. Now let me amplify that value of output so that we can see. Now at 100 kilohertz we are going to check at around 100 kilohertz. If I check the value, it is 880 millivolt. Now we are looking at the value where our input and output are same. Now I am increasing from 100 to 200. Let me increase that input 200. Our output is 420 millivolt. Now if I increase it, let me increase. See, I am increasing 300 volt. It is 300 millivolt. 300 kilohertz. Now I am going to 500 kilohertz. We will be checking the output. It is 184. It is still the input has not come. Input is 100 millivolt. Now I am increasing, slowly increasing. Now it is going to 100 millivolt. Now see around 7. Now if you see around 750, the input and output are almost same. 120 millivolt, 120 millivolt. Now this is the point that we are looking at. Means 100 millivolt we have applied, but around 750 kilohertz we are getting around 100 millivolt. Now if I check at 1 megahertz, now our output will reduce to lesser than 100 millivolt. It is around 88 millivolt. So this is the frequency analysis of non-inverting amplifier. Now we are going to look at the. Now this is the Excel sheet. This is your frequency. This is the output voltage that we have jotted down, and this is your gain how we have calculated. B2 by 0.1. B2 is this column and divided by 0.1 because this is the input, and this is your 20 log gain in dB. C2, this column is C2, C column, and at the base of 10. Now what we are going to do, we are going to select this frequency range and make a control button. Then we are going to select this gain in dB, and we are going to go on insert. If you go, we are clicking on insert. If you click on the insert and go to chart, and you will get that plot. Now this is a border plot. Now let me change to this one too. Let me change this to logarithmic scale. Now left click your cursor, format axis. When you are going to get a format axis, now if you see here, you will be getting a logarithmic scale. Now click on the logarithmic scale. We are making this logarithmic scale, and we have started taking the frequency from 50, so we are changing to 50. Now making enter. Now this is your body plot that we got. Now if you see that at 3 dB point, at 8.2 kilohertz, we got a 3 dB decay, and where we are saying that it is cutting, it is cutting around 740 kilohertz. So this is your body plot that we can draw by doing the frequency analysis. Now what we are saying, a value lesser than this one, 8.2 kilohertz, it will be like a low pass filter, and after 8.2 kilohertz it will be like an integrator, because this is the curve of 1 by s, this curve. Now actually it will be integrating around 5 times of this value. At around 5 times of this value, it will be a perfect integration. If you check around this frequency after 50,000 hertz, you will be checking that we are getting the integration. Now we are going to look at these 2 points on DSO. Before going to DSO, let us calculate the transfer function. This is the graph that we got access it from where we got this type of graph. Now at 3 dB point was 8200 hertz, and gain was 40 dB, means gain was 100. And where it was cutting the 0 axis line, this is your frequency line, and this is your 0 dB, where it was cutting around 740 hertz, 740 kilohertz it was cutting. Now this resembles to k by 1 plus tau s. Now how to calculate k? The gain is 100. Now I have taken the 100, 1 plus tau s. What is that tau? Tau is nothing but your omega at 3 dB. What is omega at 3 dB? This is nothing but 2 pi into frequency at 3 dB. Frequency at 3 dB is 8200. Now if I calculate the tau, I got 1.94 into 10 to the power minus. So this is your transfer function. Now this is the resultant transfer function, 100 by 1 plus 1.94 into 10 to the power minus 5 s. This is the transfer function of inverting amplifier with the gain of 100. Now at below this frequency, it will be passing all this value. Means whatever the signal that if I apply sine, it will be passing that value. But and after this frequency, after 8200, it will be integrating. But if I look at the transfer of k by 1 plus tau s, now when it become perfect integrator, when we can neglect 1, When we can neglect 1, when this value become very greater than 1, means at around this frequency, when this frequency become far greater than, means around greater than 5 times or 10 times, then you will get the perfect integration, because 1 by s term is coming. Where 1 by s term will come, that will integrate it. Now what is the time domain response of e to the minus t by tau? When we will feed this type of signal, a square signal, then what it will be doing, a charging and discharging will be happening till from this frequency to almost this frequency. Till this frequency it will be charging and discharging from this frequency only, but we will able to show about this frequency. We will be seeing that it will be charging and discharging, and around this frequency it will be doing the perfect integration. That we are going to look at the DSO. Now we have seen that for sinusoidal it will be passing with the gain of 100. Now I am going to put in a square. Now if you see, this is the yellow one square. If you enlarge this one, if I make this one, for negative voltage of DC it is charging, and for positive voltage of DC it is discharging. If I increase the frequency, it will be seen very easily. Now if let me decrease this point. Now if you see this, in negative DC it is charging, and in positive DC it is discharging. This is happening because of that minus sign. Otherwise in positive it will be charging, and negative it will be discharging. Now if I now see the frequency at around 10 kilohertz, it is doing same thing. Till now it is not integrating. Our point was 8.2 kilohertz. If I increase the frequency, let me increase the frequency to 37, means 5 times around that value. See, this is the perfect integration happening. Now if you want more perfect, go higher frequency, the integration will be happening, but at the same time your gain will be reduced. Initially the gain was 100, now the gain has come down, the value is 2 point. Now this is the perfect integration is happening. Means what we can say, the integrator is the inverting amplifier is acting like a integrator in the high frequency range, and a low pass filter in the low frequency range. So this is all about the inverting frequency analysis of inverting amplifier.